Hi. Thank you for those of you who trekked over here in the rain. Really appreciate that. It's great to have you here at the UCCS Speaker Series. This is the second of our 6-part series on artificial intelligence this winter. As you know, in this series, we'll be covering the basics of AI, some of the applications in health, economics, and government, and implications of AI for the economy and for our way of life in California. We work to bring you some of the University of California's leading experts on these topics in the hope that they'll provide some context for understanding what's happening and where things might go. Today, we're pleased to be joined by Zachary Pardos. Although Dr. Pardos will focus to some extent on his recent work, I think he'll leave you with a sense of possibility for how AI will change the way we educate our students, all the way from pre-K through college. Dr. Pardos is Associate Professor of Education at UC Berkeley, who studies adaptive learning and artificial intelligence. At Berkeley, he directs the Computational Approaches to Human Learning Lab, teaches in the Data Science undergraduate program, and is an affiliated faculty in cognitive science. His current research focuses on knowledge representation and recommender systems approaches to increasing upward mobility to post-secondary education using behavioral and semantic data. And if I'm translating this correctly, this is kind of like making Netflix-like recommendations for courses for college students based on their interests, current knowledge, and needs. I'm sure Dr. Pardos will correct me if I've got it wrong. His 2019 paper on course articulation won the Best Paper Award at the Learning at Scale conference. Professor Pardos earned both his bachelor's degree and PhD in computer science at Worcester Polytechnic Institute, and after completing his PhD, he spent a year as a postdoctoral associate at MIT. At Cal, again, he directs the Computational Approaches to Human Learning Research Lab, teaches in data science, works in cognitive science, has done extensive work on both theoretical and applied aspects of AI as related to education, and we're very pleased to have him here. Please join me in extending a warm welcome to Professor Zachary Pardos.
Hi, thank you for that very gracious introduction, and welcome everybody online and in person here. Really pleased to talk to a policy-oriented audience. My research, I would say, in the last 5 years has become more policy relevant in working with systems of higher education, and I'll point to different bills in the California legislature that are relevant to different parts of the presentation, but really pleased to have an audience that cares about policy here. So this will be a kind of a 2-for-1 talk where I'll be discussing an adaptive tutoring research project, and then in the second half discussing a transfer student success project, which is really about articulation and course guidance, how to come up with degree plans when multiple institutions are involved. And the two do have something in common, and I'll try to tie them together at the end. So a little bit about my lab, Computational Approaches to Human Learning, CAL. We got involved in applying AI to higher education very early on. We won 2 NSF grants in 2015, specifically to apply nascent AI that was coming out at that time. These are like image classification models that predict what's in an image, like convolutional neural networks, as well as the very beginnings of neural networks applied to big data for natural language processing, like Word2Vec. That's what was happening around 2015. One grant was to look into kind of the fundamentals of the applicability of AI to higher ed data. The other was to put it into practice, and that's where the recommender system part comes into play. How does machine learning meet practitioner? And that is typically with some kind of recommender system or decision support, or in some cases decision-making system like an automated driving system. In 2019, we started developing this open adaptive tutoring system, and that was deployed at Mission College, California Community College system. And then in 2020, we started an AI for transfer collaboration with CUNY that has extended to the City University of New York, then the State University of New York, and finally back to the Best Coast with a collaboration with the California Community Colleges. Okay, when I say AI, what am I talking about? What is the definition of AI, my working definition? Well, artificial intelligence today is almost all applications are machine learning, which is any kind of AI that learns from data. Almost all of those models are statistical models, be it an enhanced regression or a decision tree, or in the case of almost everything you see today that's AI, it's neural networks. Neural networks are the technology behind game AI that beats our champions of Go or of chess. They're behind automated driving software systems, machine translation of languages, and tools like ChatGPT. Another definition for what AI is it's anything that pushes the boundary between the tasks that computers are good at and the tasks that only humans are good at. So it's a kind of state of play of the state of the art of AI, and that's always being contested. And so the models that are currently contesting that boundary, which definitely AI is better at games than we are, like Go, which only 5-10 years ago, the best human was way better than the best AI. That's not true anymore. And now I'd say driving is being contested, right? Is AI good at driving yet? We'll see, but it will be, probably. So how good are humans at the task of one-on-one tutoring? Well, in 1984, Benjamin Bloom of the Bloom taxonomy came out with a paper comparing the performance of human tutors relative, one-on-one human tutors relative to one-on-many classroom instruction. And what he found and named his landmark paper on is 2 sigma. So there's 2 standard deviations difference in learning. You could say 2 standard deviations in, let's say, standardized test outcome at the end of the year if a student had a 1-on-1 or 1-on-3 human tutor versus if they only had, at that time, 1 to 30 classroom instruction. What he found was that teachers could get closer to that 1-on-1 tutoring efficacy if they followed a mastery learning protocol. And mastery learning was making sure that students had learned the prerequisite material, and in order to know that, they would test students as they came into class. The teacher would broadcast a kind of remedial lesson on the items that scored the lowest among the class, and then the teacher would break students out into groups to receive peer support on any other skills they hadn't acquired, and then reassess, and then go from there. And then they would repeat that process for every lesson that was introduced new into the class. Now that seems pretty exhausting, and so it wasn't, well, I guess it was somewhat long after. In the 90s, there was an effort called Intelligent Tutoring Systems to try to coordinate all of those logistics with a computer, right? Have the computer do the assessment, have the computer do the remediation, have the computer do the reassessment. You still have classroom instruction, but that was tried in 2001. And they got closer to sigma, but not there quite. But what allowed them to get close to there was using an architecture called Intelligent Tutoring Systems, which is a way of, a kind of digital pedagogy, a way of conducting a computer tutoring system. And that way of conducting and implementing a tutoring system called Intelligent Tutoring Systems has been time after time evaluated to be better than standard classroom instruction. So the addition of this kind of technology in a $10 million RAND study where they randomized at the school site level to see what the effect of the implementation of a commercial version of an ITS was, showed that there was a statistically significant difference. It wasn't nearly 2 sigma. It was more like the amount of learning, the amount of things students forget over a summer is how much the students who had the ITS gained over the students who didn't have the ITS. But even after all these results and many, many decades of seeing how effective this approach can be, there's been no open source project representing an intelligent tutoring system. So if you're an undergrad or a PhD student, grad student, or anyone at a company, and you want to make a tweak to an ITS, you have to collaborate with one of these companies. There isn't a project you can just download and make your modification. And the way grad school works, you typically don't want to waste 4 years of your grad school re-implementing something. You're not going to get papers out of that. So in part, that's the reason why it hasn't existed, which I think is a problem. Now, I just referred to open source, but there's different notions of open. There's different movements that use the word open in education. There's been massive open online courses, and they all mean something different, the open. Open there meant free access, and you have to pay a little bit if you want a certificate. Then there's been open educational resources, which is this idea that with the digitization of the classroom, if teachers want to adopt digital resources, they shouldn't all have to recreate them themselves. There should be central repositories of shared teaching materials and assessment materials. But open in that sense means free, but it also means remixable, that there's a license associated with the content that you can adapt it to your own scenario. And then open data of a number of systems that share data. Those systems that share data, anonymized data, are also adaptive systems, but none of them are open source. And none of them attach a Creative Commons to their license to their content. So if you're doing some kind of computational analysis of learning in those systems, you can't look at the content that students saw. You can't analyze, you can't use NLP on the content, because all of that's proprietary. So we saw a gap there, and in 2019 started to develop Open Adaptive Tutor, or OA Tutor. That would be open source, all of its content licensed under Creative Commons and adaptive. And so in a paper that was just recently published last year at Computer Human Interaction Conference, we chronologue this path to going from the current proprietary state of adaptive systems, education systems, to an open state. And that involved 3 years of fielding this system at a community college, Mission Community College, in 7 math classrooms with a single pilot teacher, 4 pilot researchers, and 25 content authors. And then a research through design methodology was used to gather data from all of those constituents. So they were both users and developers of the system, but they were also research subjects that helped us iterate the system. So they were co-designers and research subjects, and learners and teachers and all of that. Okay, relevance to California policy here. AB 1705 and AB 705, which 1705 builds off of, effectively eliminates remedial English and math classes at community colleges. The idea here is students shouldn't be taking courses that have no chance of transferring to a 4-year school. And the research also shows that if you started in a remedial class versus you went right into the standard transferable course class, you do not end up catching up, right? You end up the same place you would have ended up if you had gone right into the non-remedial class. So why are all these resources and FTE being used on remedial classes? It makes sense, it sounds evidence-driven, but at the same time, it doesn't eliminate the fact that some students need more support, right? So AB 1187 is an idea for giving them more support by expanding access to tutoring at community colleges. But if everyone could have a one-on-one tutor, everyone would, because that's most effective. In the Bloom study, it's 2 standard deviations. But that's very expensive, right? So the policy relevant question here is, can OA Tutor or something like it be beneficial in this scenario to augment perhaps the human tutors that are being assigned to alleviate some of those resources, since tutors are expensive? We're facing this at UC Berkeley and in the whole UC system, where recently students won a big labor battle, got a big pay raise, but now there's this conversation of, having to do the same with less, or do we do less with less? What should we do? Can an adaptive tutor be part of a kind of triaging process? And what we're looking into is, does it alleviate some of the office hours off of the TAs, right, by maybe addressing some basics? The system, as you see here in this short video, looks a lot like what you would imagine a computer tutor or web-based tutoring system looks like. A Khan Academy type thing, but there are components to the tutoring system that make it an ITS and not just a generic computer tutor. That is, it's based on these 8 ITS principles that have been documented in a number of papers, and distilling those out, it means immediate feedback, tell the student if they're right or wrong immediately, have hints on demand, scaffolding that breaks problems down into steps, collapsible help, and then perhaps the biggest differentiator of an ITS versus a Khan Academy is have a rigorous knowledge component model. So have a very detailed model of the skills and prerequisite structure of those skills in the domain, and then have a computational model constantly do mastery assessment of students' mastery of those individual skills that then guides them adaptively to successive skills. So it's meant to give just the right amount of practice, not over practice, not under practice. That's the adaptivity part. And in order to give the right amount of practice, you need to be constantly inferring what students have mastered based on their responses. So OA Tutor has all of those things, has knowledge tracing, which is kind of the state-of-the-art model used for cognitive mastery estimation. It's also what I did my PhD on, so I had a little bit of one up in understanding how that model works. The system's also open source, has an MIT license, and an MIT license just means you could basically use the source code for any purpose. You could use it for-profit purposes, nonprofit. You can make modifications to the code, and you don't have to share the modifications. The only requirement is that you retain credit to the lab for having produced the initial version of the system, but you don't have to make any of that public. The idea here is that I want for OA Tutor to represent the state of the art in best practices for computer tutoring systems as far as academia is concerned, and for anyone to be able to build on top of that, right? To kind of rise, kind of a rising tide, lifting all boats. The tutor isn't any good to anyone if it doesn't have content. So part of that 3-year process was to build 5 full semester textbooks worth of content based on OpenStax, which is a Creative Commons textbook publisher, and they allow for remixing of their content as long as you credit them, which I'm doing right now, and which we do in every single time we show an item from them. And we've taken problems from their textbook and we've added adaptive hints to it. We've added scaffolding to it, we've added skill model structure tagging to it, and that has really helped us be able to even do this in 3 years. And we have a whole ecosystem whereby undergraduates will apply to be digital tutors who help us create the content, help content, and this is just a sample of the team. We had 25 content developers in the 3 years to produce those textbooks. And one of them, Shreya Bhandari, started as, I think, a freshman on the content team, and now she's the lead developer of the software. Okay, so we had, in this data collection, 25 undergraduate students who were the content developers. We had 4 pilots in 7 courses and co-design meetings with the teacher. And the teacher conveyed feedback from the student that she received from the learning management system, from the forums, like what problems are they having, et cetera, any friction points. And then we had researchers who we gave some data to give us feedback on what kind of features would you like the system to have that it doesn't in order for you to complete your dissertation, for example, or in order for you to have a better dissertation. So we have many constituencies that we want to cater to, the teacher, the students, but then also the researcher, because we want this to be a platform that enables more innovation in this adaptive tutoring space than we've seen in the last 30 years. I won't go into detail here, but lots of things happened in 3 years from the end of 2019 till we published in 2023. And some findings from the deployment of this system, just a sample of the findings. So from the content authors, we learned that it took them about 2.27 hours to learn how to author in the system. So that's kind of the training up cost. And then it took them about 11 minutes to complete a problem in the system. And completing a problem meant transcribing the OpenStax question into our format, which is a kind of a Google spreadsheet format, and then adding hint and scaffold question. You can add a scaffold question that breaks the problem down into steps, or you can add a hint that's either an image hint or a text hint. So that process for a single problem took 11 minutes, which will be relevant in the generative AI portion. We also did a learning gain analysis of the tutor where we gave half, well, actually in this version, we gave students a pre-test in 2 different skills and then gave them OA tutor on the same skills but different questions. And then we gave them a post-test, which is the exact same as the pre-test. They didn't get the answers to the pre-test, and we looked to see what the average improvement from pre to post was. And we found that there was about a 23-24% improvement from pre to post when using OA tutor. We've since done more studies comparing to a control where no hints are given versus, the OA tutor hints versus a ChatGPT hint, and stay tuned for that. Some other results from the tutoring was that a project was getting feedback and then implementing features in response to the feedback. So the teacher wanted a dashboard. In this case, it was a she. She wanted to see the detailed interactions of each individual student when she goes to the gradebook and looks at the assignment associated with the tutoring system, and so we implemented that. You see the mastery score for the skills in the assignment here. It's solve mixture applications at 22% mastery for this student, and then you see how long they spent on every single step in the tutor where they answered wrong, asked for a hint, answered wrong, asked for a hint, answered right, went on to the next problem. Feedback we also got was that if our system was to be used in any kind of long-term basis, it had to be Section 508 accessibility compliant for learners with disabilities. And so that involved doing a self-report, a VPAT or WCAG compliance report, which is about a 14-page checklist of reporting how you're in compliance with different things, which we weren't to begin with. So for example, everything that's a graphical component, you have to be able to hover over it and have a text reader read what the graphical component is. So we added that to all of our UI. So now OA Tutor is Section 508 compliant, which I think can give teachers confidence, but also researchers confidence that when they deploy this tool and experiment with it, at least the base version that we provide them is accessible. The idea with the researchers is to motivate them and graduate students and undergrads to hack away at the system, right? Innovate, create new interfaces, create a different adaptive algorithm, create a different knowledge estimation algorithm, and then try it out. And so we've been on a tour to a number of different countries to give workshops and tutorials on the system to get people, give them a jump start. And if you go to oatutor.io, it'll take you to our Codebase homepage, and also that has a link to our tutorial as well as to our published paper. All right, so now what? That was way back in 2023. What's the new stuff? Increasing adaptivity to teachers was something that we really heard a lot about. That right now with most computer tutors, you kind of have to adopt it as a teacher, and it has a mind of its own. It has its own kind of values and agenda. Hopefully your curriculum is aligned, but not always perfectly aligned. So what we wanted to make OA Tutor is be more adaptable to teachers. Give it some kind of, for example, background of the classroom that the teacher provides, or some kind of stylistic cues, like the teacher likes to refer to things in the local environment or hometown locations when giving word problems or something like this, that the teacher could provide that, and then using AI, it could adapt the content and the help of the tutor to conform to that style of the teacher. Also, localization features, having the system be able to be deployed in other countries and other languages is something we're working on. So, I said I'd come back to how long it took students 11 minutes to create each problem. This meant that every single textbook that we provided took the equivalent of 1 year of a 100% FTE to create a textbook. So that's not very tractable when you think about extending to the other dozens and dozens of areas that OpenStax has, right? And there are, of course, many other areas besides what OpenStax covers. So this is a problem for scaling adaptive tutoring. So fortunately, in the last year, there's been ChatGPT that hit the scene. And ChatGPT is based on something called large language models, which are a form of generative AI. So can we ask these large language models to help us produce content? And can that result in us producing content faster than 100% FTE over 1 year? So here's an example of a problem where we have manual hint pathway created by humans. And you see here it gives a hint, and then it asks a question of the student. And then here's ChatGPT. And our approach to this was to generate a worked solution where it basically just solves the problem but gives the steps. And this has been shown to work, at least in algebra and several cognitive science articles. And so we produced a ChatGPT hint for all of our algebra content, but knowing that AI it's called hallucinate, which is make errors and not always give the right answer, we checked all of our produced hints for correctness before we showed any to students. And we found that those hints were incorrect 30% of the time. And this is on intermediate and elementary algebra content. So we removed the incorrect hints, replaced them with a regenerated correct hint, and then ran this study to see what the learning gain was of ChatGPT versus the manual hints. And the answer is that the ChatGPT, the AI, produced positive learning gains, but in this study, human tutor hints produced higher gains. The big result to me was that it took only 30 seconds to quality check each produced hint, right? Instead of the 11 minutes that it took to produce a problem from scratch. So that means a problem from scratch is both the hint production and the transcribing of the OpenStax problem. But in talking to the content authors, most of the time was spent coming up with that hint and not the transcription. So it's potentially up to a 20x increase in authoring speed, depending on how negligible that transcription was. A couple months ago, in follow-up generative AI work, we looked into producing the items themselves. Instead of transcribing the items from an open source textbook, what if we told ChatGPT to make an item based on certain attributes or a certain skill? And then we wanted to compare how good those items were that ChatGPT was asked to produce compared to the textbook questions of the same skill. And we compared this using psychometric measurement approaches where we gave tests to different pools of respondents and then analyzed the properties of those items for their difficulty and something called discrimination, so how powerful of an assessment item they are. And at least in this study, we found them to be indistinguishable statistically. The ChatGPT items had the same difficulty distribution and had a little bit better discrimination. However, in this work, we haven't yet conducted a dimensionality check to confirm that they're both covering the exact same skills, right, both pools. But on first glance, it appears so. So now I want to pivot from, in the last 10 or so minutes, from within class support to across class support, right? Helping students select their courses and helping transfer students in particular be able to make the jump from community college to the UC system or the CSU, or a similar scenario across the country. So AI for articulation, and then AI for transfer student wayfinding. The quick explanation of what articulation is this process of seeing if any course at institution A, which let's say is a community college, is at least 70% equivalent in the topics covered to a course at institution B, which is a 4-year school. And creating articulations, I was just mentioning offline, can seem like a kind of boring administrative task. But really what it's doing is it's creating the infrastructure, it's creating the roads between institutions that credit can travel along, student credit can travel along. So that infrastructure is essential for credit mobility. Now, you can have roads, but if you don't have people who know how to traverse the roads, don't have a map, don't have a GPS, then that's a problem. So the second part of this is you need to give students a GPS to know what courses to take that will transfer, and then what courses to take after transferring. Why is this relevant to California policy? AB 1111 requires the creation of a common course numbering system across the 116 community colleges. That means, all of the intro to sociology courses across the 116 community colleges need to be mapped to a single thing, as do all the transfer pathway courses, as do all the gen ed satisfying courses, even gen ed satisfying courses that maybe weren't mapped to a gen ed now, but will be mapped to Cal GETC, which is a gen ed standard in the future. That's not a very tractable task for a committee of faculty to do, is to map all those things. And so that is an application of AI where an AI can produce a candidate set of common course numbers that then a committee can look over and ratify. And we're working with the community college system on that very project. AB 928 requires CSU and UC segments to agree on a set of shared education gen ed requirements for smoother transfer from the California community colleges. So this is all very relevant to the policy around transfer. So to give a sense of how complicated maintaining existing articulations is, imagine our system of 116 community colleges, 23 CSUs, and 9 UCs. And now, in counting just the number of possible articulations between one community college and one UC is about 35,000 different pairs of courses to consider when you're only looking at department-to-department matches. It's 36 million between all CC's community colleges and UCs, and then plus the CSUs, plus private schools, plus out-of-state schools and out-of-state systems, forget about it at that point. And new courses get introduced every semester. Data science, right, is going to take a whole legislative effort and 5 years to do program alignment. I think it doesn't have to. So comprehensive articulation, where you're not missing things, it's somewhat easier to comprehensively articulate to your neighbor, right, who's a community college, but to comprehensively do it equitably to all schools is not possible by hand. So we tried an algorithmic approach to evaluate using natural language. Is this catalog description of a course at Berkeley equivalent, or how similar is it to this catalog description at Laney Community College? Now, only relying on catalog description has its problems because many instructors have very short catalog descriptions that maybe have gone out of date. Maybe they were never really very verbose to begin with. So basing that match just on catalog description could be problematic. But what we can do is we can use the enrollment histories as a kind of corroborating source of information that can fill in some of the blanks of information that might be lacking in the catalog description. So it's like you can use some data science methods to data mine the enrollment histories and fill in some of those kind of topical information about the course. And if you're into that kind of thing, look into this paper that documents all the plethora of information you can infer about a course just by knowing which students have taken it over the last 5 years. So I think right now, in terms of the algorithmic state of the art, AI articulation is ready to go. But in terms of the policy state of the art, which is where you all can be perhaps thinking, it's not quite ready. Because what's the role of faculty and staff of adjudicating algorithmic articulations? What's the software workflow? Every institution is at some level quite idiosyncratic in their processes. So how do you map what algorithms that like to be generalizable onto very idiosyncratic processes? That's a policy question. And so for our part, what we're trying to do to learn the policy solution is partnering with a number of system centers. So in 2014, we're partnering with the California Community College system, the Connecticut system. We've been working with the SUNY system to pilot algorithmic articulation in the various ways that they process those articulations and credit equivalencies, and hopefully come up with something generalizable, that can be a nationwide a tool of utility. So to test these things, we created an articulation platform in-house in the lab and tested at a number of schools. We had real articulation officers answer a survey here about what they find to be most difficult about their job, and the highest percentage category was high articulation workload, little articulation time, followed by finding equivalent courses. So with this kind of model, we can surface the model's best matches, like Google surfaces the best matches to a course to those articulation officers, and hopefully alleviate some of that workload by reducing the time it takes to find equivalent courses. And all that's needed for an institution to join this network, which is right now at nearing, I think, the end of its pilot research stage, is all the catalog descriptions of the courses being offered, existing articulation pairs that the campus maintains, and then optionally 5 years of anonymized enrollment histories to have that complementary source of information when the catalog description is a little wanting. Now, there is a human factor that enters into any equation when you have AI plus people. And I said AI is in part defined by that boundary that's being pushed of where tasks, there's some tasks that only humans are good at, there's other tasks that computers are now good at, and it keeps pushing that envelope. So as you push that envelope now into the realm of tasks that only experts, like self-identified experts, are good at, what's their reaction going to be, right, to an algorithm suggesting what they should do? And what is a way for it to be a kind of bidirectional teachable moment where maybe the algorithm has insights about a course that the expert didn't? How do you convey that? For example, there's some darn good statistics courses in public health. But if you're a faculty approving and disapproving of articulations, maybe you reflexively deny a statistics course if it didn't come from a statistics department. But if the AI, using more objective means of evaluation, has an explanation for why you shouldn't reject it, what's the proper way of conveying that to an expert? And we've done a little bit of research on that, and we continue to. All right, last couple slides here. That's creating the infrastructure, so the AI to create the roads where credit can travel along, but now you need the GPS. And so what we're working on with 2 schools in the SUNY system is being able to generate a transfer plan automatically for a student based on the courses they've taken so far. So we have the courses they took, let's say, in year 1 at the community college. We also have the degree requirements for their intended major at the receiving school, at the 4-year school. So let's say that's criminology. We parse those requirements. We then recommend what courses they should take in the 2nd year of the community college that are guaranteed to transfer. And then when they arrive at the 4-year school, we tell them what courses to continue to take towards degree. We're using several algorithms to do this. It's a lot of work, but Guided Pathways is an initiative to improve community college student time to degree, and I'd say it's quite effective. But I wouldn't call it a GPS. Guided Pathways is more like handwritten directions from one place to another. It doesn't recalculate. It's not dynamic. But AI can be dynamic and allow for students who take an unexpected turn to find their way back, which I think happens most of the time. So this plan generation first happened at UC Berkeley for just generating plans that don't involve transfer, and then we generated for all the degree programs at the City University of New York offline, and now we're doing a pilot where we're generating plans, first showing them to advisors to approve and add comments to, and then they would go to students after that advisor approval. So this is kind of a we have some results for AI for major recommendations, so another dimension of advising. What was interesting here is that we showed real Berkeley advisors ChatGPT recommendations based on student background. Students never received the ChatGPT recommendations, but we asked the advisors what they thought of it. And they actually kind of liked it. They were pleased, 4.1 out of 5 in terms of their satisfaction with the advice, which was surprising because the literature says experts tend to be averse to AI recommendations. So this suggests there is this room for human-AI collaboration, attitudinally. So some big picture takeaways: AI seems primed to create efficiencies in educational content production and personalization. 20x speed up, it seems, in at least algebra content. AI is also primed to be used for student and administrator decision making support. I'd say the main thing that keeps the GPS type of technology from being able to scale right now is how closely guarded and proprietary degree requirement descriptions are. They're kind of written in a proprietary system, most of them in code called Scribe that looks like COBOL programming language. You need to have experts in Scribe hired as full-time employees to translate degree requirements. And then you would think that you own those transcriptions of your own degree requirements. You don't. That's owned by Ellucian that makes DegreeWorks. So there really needs to be a push to have a universal format for that degree requirements are expressed in, so that institutions can port to a new system, a new technology, and there isn't this kind of monopoly and being stuck having your degree requirements be proprietary. Also, in both cases, there's human desire for an empirical justification for the necessity of human-AI collaboration instead of full automation. So AI gets math problems wrong. We need someone to check that. AI isn't always going to get the articulations right. We need at least a committee, to ratify that. So I think policy-wise, should be thinking of AI as a draft of something, right, that can make work more efficient and more productive by combining AI and human expertise. I hear that we're excited, and I want to thank the funders, and thank you for your time.